Cat, your friendly chemistry tutor.
VSEPR theory. Electrons kind of hate each other, but they don't want to be lonely, so they form a pair. Some would call this a toxic relationship, but this is what the valence shell electron pair repulsion theory, or VSEPR theory, is based on. Although the electrons may be obligated to like and accept their electron partner within the pair, they can still freely hate on other electrons outside of their pair. So, they will repel other electron pairs and try to get as far away from them as possible because they want more space for themselves. Cats often act similar to this. They have to tolerate their cat siblings that live in the same household as them, but they will terrorize the rest of the block to mark their territory. To understand the VSEPR theory, we first have to understand the real difference between electron geometry and molecular geometry because they are not the same. Electron geometry accounts for all the bonded groups and the lone pair groups in a molecule, and it remains the same no matter how many lone pairs are present. On the other hand, molecular geometry only accounts for the bonded groups in a molecule and ignores the lone pair groups in a molecule. I know, poor lone electrons are always feeling left out. Additionally, bond angle is a characteristic of molecular geometry. You'll see what I mean later. So why is this important to know? Well, two molecules could have the same number of electron groups or electron-dense regions. They could also have the same electron geometries, but very different molecular geometries, which results in a slightly different bond angle as well, all by including or ignoring the lone pairs. Let's get into it. Quick warning though, you do need patience to learn the following. This is the VSEPR theory chart in a nutshell. I'm going to go into detail about all of these next, but if you think you've already got it, then you can skip directly to the knowledge check near the end of this video. For a molecule with two electron groups around the central atom, the electron geometry is called linear, like a straight line. The molecular geometry with zero lone pairs is also called linear, with a corresponding bond angle of 180 degrees, just like you learned in math class. Or maybe you didn't pay attention. Whatever. Did you notice here that the molecular and electron geometry are the same? Good, because there are no lone pairs to ignore. And if we went ahead and swapped this bonded group with a lone pair group, this would result in a diatomic molecule, but both geometries would still be linear because the atoms are arranged in a straight line. For a molecule with three electron groups around the central atom, the electron geometry is called trigonal planar. And it remains the same no matter how many lone pairs are present, because electron geometry does not discriminate against lone pairs like molecular geometry does. The molecular geometry with zero lone pairs is also called trigonal planar. And the corresponding bond angle is 120 degrees. The molecular geometry with one lone pair is called bent, with bond angles slightly less than 120 degrees, because lone pairs take up more space, which reduces the bond angle. No wonder they're constantly left out. They're always getting in other people's spaces. For a molecule with four electron groups around the central atom, the electron geometry is called tetrahedral, and it remains the same no matter how many lone pairs are present. Its molecular geometry with zero lone pairs is also called tetrahedral, and the corresponding bond angle is 109.5 degrees. Its molecular geometry with one lone pair is called trigonal pyramidal, with bond angles slightly less than 109.5 degrees. Its molecular geometry with two lone pairs is called bent. so the corresponding bond angle is a lot less than 109.5 degrees. The bend shape comes from the fact that the bonded groups are hanging off the x-axis like this. It's not a very good posture, but what can we do? Stay with me. For a molecule with 5 electron groups around the central atom, the electron geometry is called trigonal bipyramidal. And you guessed it, it remains the same no matter how many lone pairs are present. Its molecular geometry with 1 lone pair is also called trigonal bipyramidal, and it has bond angles of 90 degrees and 120 degrees. Okay, its molecular geometry with 1 lone pair is called a seesaw, with bond angles slightly less than 120 degrees and also slightly less than 90 degrees. It's called a seesaw because if you look at it from this way, it looks like those seesaws from the musty playgrounds in elementary school. The molecular geometry with 2 lone pairs is called T-shaped. Why? Because it probably looks like a T. And if you look at it two-dimensionally, you'll be able to see here that the bond angles are slightly less than 90 degrees over here and slightly more than 180 degrees over here. Its molecular geometry with 3 lone pairs is called linear, and the corresponding bond angle is 180 degrees. That's because if you ignore all of those lone electron groups, this is clearly a straight line. We're almost there. For a molecule with 6 electron groups around the central atom, the electron geometry is called octahedral, remaining the same no matter how many lone pairs are present. Its molecular geometry with 0 lone pairs is also called octahedral, and the corresponding bond angle is 90 degrees. Its molecular geometry with 1 lone pair is called square pyramidal, and the corresponding bond angle is slightly less than 90 degrees, and it's like a pyramid with a square at the base. Okay, its molecular geometry with 2 lone pairs is called square planar, with bond angles of exactly 90 degrees. And the planar shape is two-dimensional compared to the pyramidal shape from above. Its molecular geometry with 3 lone pairs is called T-shaped. And the corresponding bond angle, once again, is less than 90 degrees here and a bit more than 180 degrees over there. Lastly, its molecular geometry with 4 lone pairs is linear, with a bond angle of 180 degrees. You got it! Here is your knowledge check to see if you really did pay attention. Determine the electron geometry, molecular geometry, and corresponding bond angles of hydrogen bromide and sulfur tetrafluoride. Please pause the video and return when you are ready. Welcome back! Let's look at hydrogen bromide. You would first want to draw the Lewis structure of the molecule, which I have already done here, and then you count the number of electron groups around the central atom. Although this is a diatomic molecule, hydrogen can never be the center atom, so we will just have to focus on the electron groups around bromine, which are 4. So, the electron geometry is tetrahedral. If we ignore the lone pairs, then you can see that this molecule clearly looks like a straight line, so its molecular geometry is linear, with a bond angle of 180 degrees. Great! I hope you got that. If you didn't, you're probably doomed. Just kidding. Now let's look at sulfur tetrafluoride. You should draw its Lewis structure first, and then we count the number of electron groups around the central atom, which is sulfur in this case. 1, 2, 3, 4, 0.5. So the electron geometry is trigonal bipyramidal. And if we ignore the lone electrons on the central atom, this looks like a seesaw. So its molecular geometry, yep, probably the seesaw. Therefore, corresponding bond angles are a little less than 120 degrees and also a little less than 90 degrees. Fantastic! You are now a true chemist. Thanks for watching. Please feel free to email me at chemcat786@gmail.com for any questions, and don't forget to like and subscribe for more content.